In this video, we'll be talking about Descartes' rule of signs. Now, in the previous video, we talked about attempting to determine what possible rational zeros a polynomial could obtain. In this video, we're going to go ahead and try and narrow the scope of the possible zeros we could pick. Now, the way that we're going to do this is, again, by attempting to determine the number of signs, or specifically the number of sign changes that exists in this polynomial. So, you'll go from here to here, and you'll notice that this is a positive value, and this is a positive value, again, from term to term, so there's no sign change there. But from this cubic to this quadratic, it goes from positive to negative, which means that there is one sign change that is occurring there. Then I'm going to go from here to here. You'll notice that going from negative to positive, so there's my second sign change. And from here to here is positive, so there's no sign changes there. So now this is on the original function f of x. So this is going to denote, if it's the original function, the possible, or the number, I should rewrite that, the number of positive real zeros. Okay, now I might abbreviate this as the number of PR. Let's see, I don't really want to use zeros because I don't want to make this seem like it's a PRZ situation. This is, I should rewrite it as this way: the number of positive real zeros. Okay, so this is my notation that I'm going to use when I'm trying to denote how many, or up to how many, possible rational zeros there could be. Now, Descartes' rule of signs specifically says that the number of positive real zeros that this polynomial can obtain, or will obtain, is either equal to the number of sign changes in total, so 2, or some number less than that after subtracting an even number. So, if I get 2 sign changes, if I subtract an even number from this, I get 0 sign changes. Now, the idea is, can I subtract any more even numbers from this? And the answer is no, because if I get to a number of zeros, again, a number of these positive zeros, then it's either going to be 2 of them, 0 of them, or, again, 0 denotes none. We're not going to have a negative number of these things occurring. So, I have 2 or 0. This is the exact number of positive real zeros that this function should obtain. Again, now notice the difference between real and rational. In the previous example, we talked about rational. In this one, we're talking about real, which means that if I don't have real zeros, these 2 positive real zeros, then the implication is I don't have any of these positive real zeros, and either they're going to be negative, or they're imaginary values, in which case this should be able to factor, not factor exactly, but we use the quadratic formula to determine those values. Now, we still haven't figured out the negative, the number of negative real zeros. Well, to do that, now keep in mind I'm going to go ahead and put that in a box, that's part of my answer. To do the negative real zeros, I'm simply going to go ahead and evaluate what is f of negative x, which is simply going to replace all of my x's in this problem with a negative x, and then I'm going to go ahead and simplify all of these terms. Now, it doesn't just simply change all of the signs in here, it only changes the signs that are odd powers, because a negative to the power of 4 is still going to be positive. So this doesn't change that term. But in here, a negative x to the power of 3 is going to change it to a negative, which means that this sign out in front will change to a negative instead of a positive. Again, this is here negative 40, and because it's a squared function, this is going to leave this as a negative 40x squared. Again, it's going to change this to a positive x, and that means that this is not going to change at all. Then back here, I'm going to have a negative 38x, and finally plus 12. So now in this example, I'm simply going to, again, one more time, count the number of sign changes going from one step to the next. It's going from positive to negative. There's one sign change, none there, and one there. This gives me, again, one more time, a total of 2 sign changes in this function, and the rule remains the same. The number of negative real zeros is going to either be the number of sign changes or, again, 2 minus the number of those sign changes, so 0. So, in this case, that means I could have 2 positive real, or I could have 2 negative real, or in some case I could have no real whatsoever, and this is not going to factor, and therefore will only provide me with imaginary values. Now, if I were to rewrite, let me go ahead and give one more example here so it's clear. Let's say I have f of x is equal to 3x cubed minus 2x squared plus 4x minus 2. You'll notice in this example that I'm going to go from positive to negative, from negative to positive, and from positive to negative. There are 1, 2, 3 sign changes. So 1 from positive to negative, negative to positive is 2, positive to negative is 3. There are 3 sign changes in the original function. That means that the number of positive real zeros will either be the number of sign changes, 3, or it will be a, again, number of sign changes that is less than that, such that we're subtracting an even number. Well, the only number I can subtract from 3 that's even is 2, so that I don't get a negative number. So I'm going to go ahead 3 or 1 positive real sign changes, or positive real zeros. So again, the implication is that the number of sign changes I have, let's just say for an example, if I had the sign changes was equal to 7, then this would imply that the number of whatever zeros that I'm looking at are 7, or 5, or 3, or 1. Okay, I don't know exactly which one of these is going to be, but it could be one of these. Now the big scheme as to why this is important is, let's take a look at this back example right here. You'll notice that this is the function we originally started with in the previous video for the PRZs. This is the list of possible rational zeros that we found. In here, this is my Descartes rule of signs. If either one of these two cases came out as 0 and didn't have any sign changes at all, then you should be able to recognize that if the possible positive rational zeros, or real zeros, is 0, then from this entire list I could remove all of the positive options and only test the negative options. Again, this is the reason why Descartes' rule of signs is so effective, because it could potentially remove a whole large chunk of values that we no longer will have to test to find our zeros. Secondly, if I go ahead and I test one positive real zero and I find a value that's going to work, well, by finding 1, since the option is from 0 or 2, then by finding 1 tells me that I've got to find a second positive real zero that's going to also work. Okay, so again, based on the way these sign changes work, it will determine exactly what I should test in here. Now on a problem like this down here with 3 or 1, I can guarantee that this function right here has to have at least one real zero, and therefore I should probably be testing the positive cases first and not necessarily the negative cases. This is again the grand scheme of Descartes' rule of signs and why it should be used to make things efficient.